So what this says, when a line is drawn parallel to the side of a triangle and then it intersects the other two sides. So what that's referencing, what I kind of sketched out yesterday, here's our big triangle. And then what that first sentence is telling you is if we draw in another line that's parallel to one of the sides. So if you look at these little arrows here and here, those two lines are parallel. So what I did is, and what the sentence is telling us is, if we take another line and draw it in so that it's parallel to this line. Now I could do it down here, but notice how it doesn't intersect that triangle. So the second part of that statement is not only do we need to draw a line that's horizontal to that or parallel to that line, but it also needs to intersect the other two sides. And that's specifically what this line right here does. So these are parallel lines. So that's the line that we drew in parallel. It's parallel to this bottom side, and then it needs to intersect the other two sides. So this side and then this side. When that happens, similar triangles are formed. So the similar triangles are, we have that big blue one, and then what we would also have is, red, since it's red, is we have that smaller red one. So the big blue one and the small red one are similar triangles. There we go. All right, so with that, it says, for this example, give a similarity statement then, since we have two similar triangles, give a similarity statement for them. So what we got, you may have this down from yesterday. I'm going to write the big blue triangle. I'm going to go down the big blue one from A to C to D. That then should be similar to the red triangle, and we definitely need the A to match up. And then we would go kind of that same direction, A to B to E. All right, that makes sense. Follow that from yesterday. Then I want you to find the scale factor. So if I want you to find the scale factor, if we're going to split these up, and I talked yesterday about we have split these up in the past, we have done a couple. Long term, we don't necessarily want to be splitting all of these up, but if you did split them up, it's not wrong. It's just going to take a little time, and you're going to start seeing more and more of these. So long term, it's not a particularly efficient thought process, but it would certainly work. So what we want to do in terms of the scale factor is if I had two triangles, I want to make sure I have corresponding sides, and I need to know lengths of both of them. So the sides that I know the lengths of both are the right-hand sides here. So if I do the big blue triangle, actually let's do the little red one. So the red triangle's right-hand side is a 5. So I'm going to do the red one, 5, and I'm going to compare it to the right-hand side of the big one. So the big one is that blue side on the right-hand side. This is Cam at home today. All right, so this is kind of what Cam and I went back and forth with yesterday. How can we figure out the length of A to D? Well, from A to E is 5, and then from E to D is 3. So if I want this entire length, wouldn't that entire length then be 8? So our scale factor is 5 to 8 if we go small to big. All right. Then I said, all right, well, let's set up a proportion. Actually, now that I look at this, I feel like we didn't do that yesterday. I must have skipped over that. So now if we set up this proportion, this is what we did yesterday. So hopefully, again, now this will make sense and you can actually read what I'm writing. To set this up, we want to take one set of corresponding sides that we know. We know that. We know these two sides here. The red triangle has a right-hand side of 5. The blue triangle has a right-hand side of, and then I told you yesterday to maybe write this initially as 5 plus 3. That's how we're going to get that 8. You can certainly write it as 8. I'm going to erase it in a second, and I'll write the regular old number 8. But the reason I kind of like you to write that initially, when we go to the other side, if I want to solve for x, which is what this one is asking, x is the left-hand side of the blue one, or I'm sorry, of the red one, the smaller one. So that has to go on top. And then what I should be putting down here is the left-hand side of the big triangle. So just like you would have done on the right side, don't we take the 5 and add 3 to it? So if I'm going to figure out the left-hand side of the blue one, I'm going to take this length from A to B, which is x, and then I'd have to add an additional 2 to that. All right, does that make sense? Now I can actually see people got that. At that point then, let's go ahead and write this as an 8. We solved this yesterday. The proportions we should be pretty good at now. So if this is now an 8, we said we're going to cross multiply. So that's a 5 times x. Come on, you. I just have to make sure the pens work. There we go. 5x, and then 5 times 2 is a 10. The 8 times the x would have been 8x. And then when we solve this, so subtract our 5x over, what we got was 10 is equal to 3x. And do this over here. That's why you should have a 10/3 written down from yesterday. All right. Then we talked about y. Y is the base of the small triangle. So I'm going to take the base of the small triangle, y. I'm going to compare it to the base of the big triangle, which is 10. And then now on the right-hand side, let's go ahead and basically set up the same thing. Don't we know the right-hand side would have been 5? That's the right-hand side of the red one. And then the right-hand side of the big one is an 8. And then, Ahmed, did you say couldn't we use the other side now too? Or ask why don't we? Yeah. Now that we know this is 10/3, you could, if you want, do y over 10. So base to base. And then now I could do the small blue or small red triangle, which we know is 10/3. And then do 10/3 plus 2 to get this full side, but that's kind of messy because there's just fractions in there. But we now would be able to do that. This one though is super easy, so let's do this guy. So crisscross those, you're going to get 8y equals the 50. Divide by 8, that's what, 6, 2 left over, so 6 1/4, and then y ends up being 6.25. That's where we left off yesterday, largely. All right, good with all that. Now we feel better about this, hopefully. I do. All right. However, there is a shortcut for one of those problems, and specifically there's a shortcut for us being able to figure out what x is, and it's called the side splitter theorem. The reason it's called that is because we are basically splitting the two sides with this parallel line right here. So what this says, same exact first line at the top of the page. If a line is drawn parallel to the side of a triangle, so that's this red line that we talked about in the original problem, and it intersects the other two sides. So this red line right here satisfies what I have highlighted in blue down here. Then, and I don't know if you got this down yesterday, then it intersects those two sides proportionally. Proportionally. Is that how you spell it? What did I say?
Almost the same.
Okay, so I use intersect versus divide yesterday. So we'll say those are synonymous. All right. Yeah, same idea. It's going to divide those two sides proportionally, or intersect those two sides proportionally. Okay.
You told us third side, so we change that to side.
Say that again.
Because yesterday you said third side divides these two sides proportionally. Should you just take out the third side part?
Did I write something about? Yeah. We don't want the third side. This line right here. So let me show you this one. Here's this big triangle. Here's the triangle that we're referencing. And then we have a line that is drawn in parallel to one of those sides. There we go. So that's the line in between the circle and between that triangle. And notice how it is parallel to the third side and it intersects the other two sides. So this red line should intersect these two sides or divide them, all right, split them, however we want to word that, those two sides proportionally. What that simply means, and we're going to do this one two different ways. Actually, I'll do the previous problem with this rule to kind of show how this would work for this one. Notice how this is our big side on the left, big side on the right. It's going to split these proportionally. So what that simply allows me to do is write this as 4 over 1. That would then equal, remember what a proportion is, 6 over x. You could, just so we understand, we can go about it a little differently. we could go, since I went the left-hand side of both, small left-hand side, big left-hand side, and then small right hand, big right hand. We could also just do exclusively the smaller side. So we could go 4 to 6. So small left, small right. And then do this down here, go 1 to X. So both of those set up nicely. This is how, as we move forward in this, I'm probably going to use this first one. I kind of like just going 4 over 1, 6 over X. But both of them would work, because if you notice, when we crisscross, we get a 4X here. If we go to the other version, crisscross, you're going to get a 4X there. The 1 and the 6 make a 6, and then same product over here equals a 6. So whichever one you see better, whichever one is going to be easier for you to recognize and do, it doesn't matter. Divide those. 6 divided by 4 is 3/2, or 1.5. So then we know that this is 1.5. Good with that. Any questions on that? All right, then, before we do y, pop up back to this first problem then, and let's use this theorem on this problem. Because shouldn't we get x to be a 10/3? We already know that x is a 10/3. But if we use this theorem, then we should be able to do this, in my opinion, a little bit quicker and a little bit easier. So here is the line. It'll stop spinning. Yeah, so here is the line that we can use the side splitter theorem for. It's parallel to the third side. It should divide these proportionally. So now just do x over 2 should equal 5 over 3. Crisscross, multiply, 3x equals 10. Divide, doesn't that tell us that x is in fact 10/3 as well? The same thing that we got over here by doing these with a different proportion. All right. So that's the side splitter theorem. The thing to be careful of, that just works for the sides, not the one that it's parallel to. So when we now go down to this one, we still need to figure out what y is. Now we do need to kind of go back to what we would have normally have done. So I'm going to take the small side, or the small base, the small bottom, which is 9. I'm going to compare it to the big base, or the big triangle's bottom of y. So remember what I did? I did small over big for the triangles. Set up the right-hand side. Seems simple enough, and be very, very careful how you set this up. All right, I have 2 years worth of trust in Jenna. So you're not gonna let me down, right, Jenna? Good, I knew it. So Jenna said 4, so she chose this side right here, and then she put it over 5. All right, do we understand why it's 5 and not a 1? The side splitter theorem, you just go 4 to 1, right? We just went over here, 4 to a 1. Now we need the big side of the triangle. So this entire big side is the sum of 4 and a 1. So you needed to add those and make it a 5. Anybody do it differently and think they're also right? So 9 over y. Anybody else do a different route? Because this is Ahmed's question, kind of. Cam?
I didn't, but could we do over 6 and then 6 plus x?
But don't we not know what x is?
Oh, 1.5?
Yeah, so we could do over 7.5. Yep.
Yeah.
So you could also, now that we know both sides of all of them, we could have done this. This is probably what I would have done, what Jenna had here. And then we just go ahead, solve that, and then we're on our way. All right. So 4y, what is that? 11 and a quarter. Promise you solve this one, you're going to get 11 and a quarter. All right. All right. So now let's go to these and let's see if we understand how we could set this up. What I want you to do first in this one is actually solve for y first. Actually, maybe let's just do this one together. It's a big jump for the first one to go through. So let's say I want you to solve for y first. So here's why this is why we can talk about the side splitter theorem. Here's our triangle. And then here is the line that gets drawn in parallel to one of those sides. So now parallel, parallel. So the sides that it is dividing, that it's splitting, intersecting, whatever word we want to use, those are the ones that are in proportion to each other. So since this line creates a 3 here and a 5 here, we could just say 3 to 5, and then go to the other side that it's cutting, that it's splitting, and do 4 to y. And then very quickly, we have the value of y. So that's the side splitter theorem. It only works for those sides. So 3 times y equals 20. All these decimals, you're going to have people freaking out here. Should give us, what, 6 and 2, so 6.6 repeating. That's the length of y. There is no shortcut for the base. It's the whole little small versus the big, and then doing the same thing on the other side. So this one we have now done a couple of times. Set up an integral that will give us x. So this was y. Now set up an integral, or not an integral, wrong class. Set up a proportion that would give us x. All right, Cam, what do you think, Cam?
8 over x equals 3 over 8.
You're close. So here's what, see if anybody can tell us what we need to correct about what Cam just told us. If I wrote it down right. So you said 8 over x, and then you put 5 over 8.
No, 3 over 8.
Okay, so let's see if we understand why this isn't quite right. Can anybody tell me why this isn't quite right? Whose hand is it? Alexandra, what's our issue?
Does it have to be x over 8 equals like 3 over 8?
Why is that, Alexandra?
Because I did like small over big.
Okay.
For both.
Good. So let's look at what Cam has, because Alexandra is correct. And then Cam, see if you understand this. Isn't 8 the big side? And we compared it to the small side. So you did big over small. When we come to the other side, isn't 3 the small side? And then the 8 the big side. So did we have the same relationship in the numerator and our denominator? No. So Alexandra said she moved these around. She did x over 8. So she did small over big. So what Cam could have done, since he established this as his first fraction, there's nothing wrong with that. What you would then have to do is flip these guys around. So if we now flip it, put the 8 on top and the 3 on the bottom, then we would be good. Alexandra had it different. She put x over 8, so she went small to big. So then over here we go small to big. Either way, that's going to get the same product and the same answer. All right. All right, so solve that. What do we get? 8x. All right, now we finally get a good number. 8x equals 24. And then x should be 3. All right, give you 1 minute. Do both and B. So get x, get y. See if we're catching the drift of all these. Okay, give me about 30 more seconds. Hopefully we're getting close to these two answers. All right, can you give me something for X? Cam, what do you think?
Would it be X over 2 instead of 8 and 10 over 3?
Good. X over 2, 10 over 3. That's how I kind of see it. You could do X over 10, 2 over 3. That's the other route we can take, but I like doing that the way Cam did. Just X over 2, because it basically sets up as a fraction itself, right? The X is on top, 2 is on the bottom. It just looks nicer. Crisscross, multiply. What'd you get, Cam?
6.6 repeated.
Good. Should get 6.6 repeating. 20 divided by 3. All right, so that's this. Or 6 2/3. 20 thirds, however you want to write it. All right, then we go to Y. The Y is the one that typically causes a little more issues. So let's just see what we got here. All right, let me get that. Aquaman, what do you got? Give me the proportion. Yeah, how did you set it up? Good. So he did the small base, compared it to the big base. So that's the Y over 18. And then he did the small right-hand side of 10. You might not have heard him at home. Then he said 13 because that's the big right-hand side, the sum of 10 and 3 together. All right. Good. And then solve that. So 13y equals 180. All right, now give me that. Aquaman, what was that? 13 and 11/13. Yeah. Whatever that decimal is. Or you can just leave it as 180 over 13. That's a perfectly valid, acceptable answer. You can give me that decimal. There's some different routes you want to take there. Oh, good. So here's what Ahmed just said. We just did it this way. I'm going to guess most people did it that way. The other way that I mentioned, just to kind of show you, is the X compared to the 10. So I went left to right. So I do 2 over 3. Crisscross, going to give you the exact same answer. He actually did it a third way. The third way is basically the first problem at the top of the page before we knew about this little side splitter theorem, is how he did this one. So let's, as a little refresher, Ahmed, if I can erase this. I'll just cross it out. All right, what's your third way? What did you do? Good. Wouldn't that also be acceptable? He did the small left-hand side of X. The big left-hand side is these added together. So X over plus 2. Then he did the small right-hand side of 10, and then the big right-hand side would be a 13. We'll give you the exact same answer. That's really what we did at the top of the paper. If you look at problem number 1 that we introduced all this with, that's what we did at the top. All right, so good. To me, it's a little bit more work. The side splitter theorem is pretty quick and efficient, but this is 100% correct, so totally fine. It works, yep. Okay, I was going to say, I think we get a little different here. So one more, letter C, do letter C. Make sure we got a handle on this, because then things get a little different on the next page. as you are hopefully wrapping up, basically the same problem. Instead of assigning variables, we're just giving you the lengths. So when you see the B to the E with no arrow on top, ray or whatever, it's just the length. So we want the length of B to E. So we want this guy right here. All right, for the first one. Christian, what do you have now? Yeah, give me the setup. Good. So he went 9 over the 6, which means so we went from here up, so then we better do the 12. And then what did you put this as? Okay, then he assigned a variable x to that length. All right, and then from there, crisscross, this actually works out nicely. What should we get, Christian? Good. And then x should have equaled 8, so the length from B to E would have been an 8. All right. And then the last one, Megan, what do you think?
I got, like, you want the,
Yeah, give me the proportion.
I got 6, I did 6 over y equals, wait, no, y over 6 equals 15 over
Okay. She changed her mind here. So she said you did y over 6.
Yeah.
All right. So A, B, what she's basically doing is A to B, she called y. So she did the big base to the small base, so big to small. And then what'd you say here?
15 over
Good. And then 15 over 9. My guess is that looks different than a lot of yours, but it should be the same. She went big to small, so then the big top side is 15, and then the smaller one is going to be the 9. Either way, when you set this up, you would eventually get 9y equals 90. And what'd you get?
10.
Good. And that should have given you a 10. All right. Okay, hopefully that now makes some sense. When we go to the next page, we'll get this started. We'll introduce this today, then I kind of figure this is a 2-day set of notes. So it says we have a similar result when parallel lines are cut by transversals. So what we've been dealing with initially is the idea that if we have a triangle, if I draw in a parallel line to one of the sides, then these guys are, these A and B, are in proportion to each other. This says we have a similar result when parallel lines are cut by transversals. So here's our parallel lines. And then here are these transversals that are cutting through them. When we finish in these notes, then the transversals. All right, Ahmed, what word do you like the best, Ahmed? Divide, intersect. Intersect, okay. Then the transversals intersect the parallel lines, not shockingly, since it says it's a similar result, the parallel lines proportionally. All right, so understand now what that means. Here are these 3 parallel lines, 1, 2, 3. It divides these guys up proportionally. So it's almost the exact same thing as if this was a triangle, where you would just do x over y, a over b. You're going to put p over q would have to equal r over s. Hence the reason we say it's a very, very similar result. So with that in mind, we'll do one of these and then go with this tomorrow. So number 2. Flipped it a little bit, right? But here's our 3 parallel lines, and then here is one transversal. Here is our other transversal. So then notice what it has done. It is intersecting those parallel lines, and from here to here, those should be in a proportion, x plus 4 over 10, at the same proportion as the 2x is compared to the 12. So pretty simple little setup. A little messier equation to solve here. So you do your 12 times the x plus a 4 equals a 20x. Just work your way through solving this. You're going to distribute 12 and x, 12 and 4. divide, or no, not divide yet, subtract the 12x over. Divide, and x should end up being a 6. Okay? So that's, we don't necessarily call it the side splitter theorem because that's specifically for a triangle, but it behaves pretty much the exact same way. All right? Okay, so with that, we'll stop there. It gives us something to do tomorrow to eat up most of that time. And you'll see some of these. Letter C is a fun one. And then we have a third page, and we'll get you some homework on all of this tomorrow. All right, so you're clear tonight. All right, if you're at home, you're free to check out. All right, have a good night. We'll see you guys tomorrow.